Alrighty, so hello everyone. This is Akash and welcome back to yet another video. And I hope you are all doing well. And I'm back once again. And just a minute, the camera is actually tilting. So this is a new setup again. And I bought a couple of gears. So I hope find it easier to study now. So yeah, that is my motive. Also, I have been a little inactive on my YouTube. So that is one thing, but I hope you'll manage. And yeah, what you'll manage, but yeah. And yeah, today I'm gonna be teaching binary lifting, and it is an advanced topic, but I think you will find it just as easy as yet another topic. So I'm excited for that, and I hope you are all excited as well. So yeah, definitely let's go and let's jump right into the video. Let's go. Alright, so binary lifting. What exactly is binary lifting? So by lifting, what does it ring you, right? So what the hell is exactly to lift, and how is the term, like what the binary term is actually doing with the lifting? So yeah, we're going to be studying everything regarding binary lifting, and it is not as hard as you might think it is. And yeah, once you understand it, it is just as easy as just another topic. So I think we should start without further ado. And yeah, I've written down a very important point over here, that is learning more topics will not make you smarter, solving hard problems will, which I definitely agree. And let me know if you agree as well. So yeah, let's go. So yeah, we're going to be seeing a problem, and yeah, here it is. This is the problem. Cool. So we have been given a rooted tree. So we have been given a rooted tree with n nodes. So with n nodes, along with that, we have been given q queries. So we have been given q queries in each query. So now in each query, we have been given two nodes, u and v, and we need to calculate the lowest common ancestor between u and v. So there are like q queries, and in each query we have been given two nodes, so u and v, and we need to find the lowest common ancestor between u and v, right, for all the queries. So now we need to do this problem, and obviously q is up to 1e5, 10 to the power 5. Okay, just a minute, I'm getting a little used to iPad. Let's choose blue. Cool. Okay, so queries can be up to 10 to the power 5, and the length or the total number of nodes can be up to 10 to the power 5 as well. So like if it's a skewed tree, right? So let's say, or not a skewed tree, but a normal binary tree. So something like this thing. So 1, 2, and 3, 4, 5. I'm just drawing a random tree over here. 6, 7, 8. So like this is a tree, and now let's say we have been given a query. We have been given this fourth node, and say seventh node, and now we need to calculate what is the lowest common ancestor between 4 and 7. So how exactly would we do it? And if we try the brute force way, which is the order of n way, to calculate the lowest common ancestor between these two nodes, then order of n will be required to calculate this lowest common ancestor, and for each of the query, that would make our time complexity equals to order of q into n. So for each query, we will run this order of n operation, which is the brute force way that we learned while learning the binary tree. So yeah, that is not optimal, as you can see over here. Q is up to the 10 to the power 5, and n is up to 10 to the power 5 as well. So that would be 10 to the power 10, which is obviously much larger than what the compiler could handle, right? So like we need something else. So what we would do? Alright, so here is exactly how the binary lifting idea comes. So binary lifting, we use this topic to find quickly the lowest common ancestor. So to quickly find the lowest common ancestor, we use this technique. So like if you know about binary exponentiation, that would generally help, but don't need to know about it but let's discuss as important thing, that is every integer, every decimal number, like let's say 14, can be represented in binary. So the binary representation for 14 would be 1110, right? So every number, that every number could be represented in its binary representation, right? Okay, cool. So now let's say I've been given 13 and I need to find the binary representation for this number. Cool. Now let's say we have been given this bits, right? So like when I'll take logarithmic of log base 2 of this 13 and seal this, I will actually get the highest power of 2 that could possibly be turned on to get 13, right? Do you guys agree? So that would be, in this case, 2 to the power, this will evaluate to 4 as 2 to the power 4, 2, 4, 8, 16, that would be 16, right? So actually 16 is larger than 13, so 16 will not be turned on, but just in case we take the seal, right? So 4 would be the answer over here. So these are the bits, let's say. So in general we are saying the fourth bit is the largest bit which could be turned on to get a 13. It doesn't make much sense to turn on the bits after that. So because 2 to the power 4 is larger than 13, so 2 to the power 5, 2 to the power 6, all those numbers will be larger than 13 as well, right? So it doesn't make much sense to turn those bits on. That's why we're doing log base 2 of 13 and sealing that. Okay, so now we need to construct the binary representation of 13. Now we start with this exactly this thing, the seal of what we have got. So this, let's call this x. Okay, so now let's see 2 to the power x. So let's say let's do 2 to the power x is 2 to the power 4. Now let's get x was 4, so 2 to the power 4 is 16. We see that 16 is larger than 13, so we don't do anything, we just decrement x by 1. So now x would become, instead of 4 it would become 3. So now we are here, right? Okay, so now what we'll do, we'll calculate 2 to the power x, which is 3, which is 8. So 8 is lesser than 13, so this bit would be turned on. So let's turn on this bit. We have turned on this bit. Cool. Let's move on to the next bit. So we'll move on to the next bit. So this would become 2. This would come here. Now we have added a 8 over here. So now 13 minus 8 would become 5, right? Because we have already added a 8. So now this is 5, right? Okay. So now 2 to the power x, which is 2 to the power 2, will evaluate to 4, which is lesser than 5. So we'll need to turn on this bit. So we'll turn on this bit. Cool. Now we'll decrement x further, which will become 1. Now we have added 4. We have made a 4 also. So we'll subtract 4. This would become 1. Right. Now our pointer will move 1 step backward, which is the 2 to the power 1. Okay. Why is this not going, man? Okay. Okay. So now 2 to the power 1 is 2, which is greater than this thing. So we'll not do anything. If it is greater, we'll not do anything. We'll just simply decrement x further, so which is 0. Now 2 to the power 0 is 1, which is greater than equal to, which is exactly equals to actually this one. So now this actually is 0 because we didn't do anything. And now we are over here, 2 to the power 0 is 1, which is equal to this. So we'll turn on this bit. And now we have made our the binary representation of 13. So if you'll see, 1101 is the binary representation of 13. So why I'm telling you this, you'll understand in just a minute. Okay. So now I hope you understand this. Okay. So to understand binary lifting, what we exactly do is we calculate a 2D matrix. A 2D matrix, let's say up of u and I. So u is the node over here. So this u is a node and I is the 2 to the power I. So we store the parent of u in terms of 2 to the power. So let's say up of u of 0 is the 2 to the power 0th parent, which is the first parent. Up of u of 1 is 2 to the power 1th parent, which is the second parent. Up of u of 2 calculates the 2 to the power 2th parent, which is the 4th parent. Or in other words, if this is u, let's say if this is my node u, and this is say a 1, 2, 3 and 4. Cool. So this thing will store this one, right? This is 2 to the power 1, which means the second parent to u, which is this thing. Cool. This will store the 4th parent, which is this thing. So we store the parents in terms of 2 to the power for each node. So this is for you. Similarly, we'll store this for 1 as well. So we'll store this thing for 1. So up of 1 of 0, up of 1 of 1, and up of 1, up of 1 and 2, right? So similarly, we'll do this for 2 as well, we'll do this for 3 as well, we'll do this for 4 as well. So we're storing all the parent nodes in terms of 2 to the power. Why exactly do we do this? You'll just understand in a bit, right? Okay. So now, what is the dimensions, or what are the dimensions of this array? So there are, as I said, we'll do this for all nodes, right? So how many nodes are there? There are n nodes, right? And how many, what is the highest power of 2 till which we need to calculate this parent, right? That is exactly what we saw over log base 2 of n and ceiling of that, right? What we just saw. So that is the highest bit that could be turned on to get this possible number, right? So that is why we do log base 2 of n and the ceiling of that. That is exactly the dimensions of this thing. So that is n into log base 2 of n. If you write it generally, that is n log n is the dimension of this array, and to calculate the lowest common ancestor, we can do this in order of log n, and we'll see how exactly we can do this in order of log n, right? Also, this operation was in log n, if you'll agree with me. If we are constructing a binary representation of any number, this is order of log n, right? Because we are iterating on the bits, right? We're not iterating on the numbers, we're iterating on the bits. So we're decrementing directly by 2 to the power, right? We're not decrementing anything by 1 or something like that. We are checking 16, then we are checking 8, 4, 2, 1. So that is what it is, every time it is halving, right? By half, by half, by half. That is exactly what that is log base 2 of n, right? Okay. So I hope you get a general idea. Now we'll see exactly how it works, right? Okay. So one more jargon that you need to know before you understand this is, let's say I have a node x. Okay, I have this node x, and I need to check if this x is an ancestor of another node, which is say y. Okay, y. So I need to check if this x is ancestor of y. How exactly would we do this? So one way of doing this is how we generally do this in pre-computation of this particular binary lifting is we initialize two arrays, which is the enter and leave time. So enter time and leave time. That is when at what particular time do we arrive at this particular node, and at what particular time do we leave from this node. That is, the enter time is the time at which we arrive at this node x, and the leave time is the time that we leave from this node x, right? So one way of calculating if x is an ancestor of y is the enter time of y is greater than enter time of x, and leave time of y is lesser than leave time of x. So mathematically, ey is greater than ex and ly is lesser than lx. So it makes sense, right? If x is the ancestor of y, so say if x is the ancestor of y, we must arrive at x first, right? So ey we must arrive at x first, right? So if we arrive at x first, the time will be lower, right? That is why ex is lower than ey, right? And if x is an ancestor of y, then we will leave y later, we will leave x later than y, right? Because if we are running a DFS, right, so it will first visit all of its children, right? So it must, if it is visiting all of its children, then it means that it will visit y also. So if it will visit y, that means that the leave time of y will be before the leave time of x, right? That is why exactly we have written ki leave time of y is lesser than leave time of x, right? So we have two arrays, enter time and leave time. So if we need to check if a node is an ancestor of any other node, or if a node y is ancestor of node x, then we'll just check if ey is greater than ex and if ly is lesser than lx. That is how exactly we will do this. Okay, so now the main thing come ki how exactly would we calculate the lowest common ancestor of uv, right? How exactly would we do this? So to calculate the lowest common ancestor of uv in logarithmic of n, first we'll check if u is a direct ancestor. If u is a direct ancestor of v, wait just a minute. If u is a direct ancestor of v, or v is a direct ancestor of u, direct ancestor of u, sorry for bad handwriting by the way. So cool, okay. So if u is a direct ancestor of v, or v is a direct ancestor of u, that means one of it is lowest common ancestor, right? Ki let's say we need to calculate the lowest common ancestor between l and x, x and y. So if x is a direct ancestor of y, in that case we'll return x, because x is an ancestor of y. So if x is an ancestor of y, then that means x is the lowest common ancestor between x and y, right? Similarly, if y would have been the ancestor of x, then that would mean that y is the lowest common ancestor between y and x, right? But if such a case comes, let's say this is my x and this is my y, then what is my lowest common ancestor? Now tell me, right? Because now x is not a parent of y, or x is not an ancestor of y, and y is not an ancestor of x, right? So now to process these type of queries, now we'll utilize this up array, right? Okay, so how we will do this, we'll see. Okay, so now as we have how many nodes in here? 3, 2, 5. So we have total 5 nodes. So what would be the highest power of 2 that could be there? It's a log base 2 of n, or log base 2 of 5 ka seal. Log base 2 of 5 seal to this, which is 3. Cool. So our array would be of size n into 3, or 3 plus, let's do 3 plus 1 because 0 is a valid thing as well. So 4. Okay, so this is the dimensions of my array. Cool. So now we have, let's say we have constructed this array, we have stored these elements. For this node I have stored the first element, the second element, the fourth element, the 8th element, the 16th element, or the 16th parent, right? We have stored all of this thing. We're storing, as I said, we're storing the parents in terms of 2 to the power, right? Okay, so my x was 3, which was the highest power of 2 that could be there. Okay, 2 to the power 3 is 8. As you can see, 2 to the power 3, which is, let's say okay, how do I put this? We need to find the lowest common ancestor between x and y, right? So now I'll start from 3, which is the highest power of 2 that could be there. So I start from 3, which is 8. So I'll go 8 places above to this and 8 places above to this, which means I'll check the 8th parent from this node and from this node, right? Now the catch is it doesn't have the 8th parent, right? So we'll see how exactly do we handle this. One way to do this is this is the second parent, and since there is no more nothing more than this, so this is the second parent. Now this will be the 4th parent, this will be the 8th parent, this will be the 16th parent, because there is nothing more than this, right? Okay, so one way to do this is that only, right? Okay, so now we are checking the 8th parent of this thing and this thing. Now say we follow my what I have said, and this is the 8th parent. Now we check ki if this node is the direct parent of x and direct parent of y, and we see that it is true. It is the direct parent of x and it is a direct parent of y. So now what exactly do? We decrement this by 1. What do we decrement? X. So x was 3 right now. We decrement this to 2. Cool. Now we check 2 to the power 2 is 4. Now we check the 4th parent. 4th parent is this only. So is the 4th parent a direct is the 4th parent a direct ancestor of x and a direct ancestor of y? Sure it is. Right? So in that case decrement x further. So we'll decrement x further, right, to 1. Now we'll check 2 to the power 1th parent to x and y, which is the second parent, right? Now the second parent is this node and second parent of y is also this node. So is this a direct ancestor of x and y? Sure it is. So in that case do what? Decrement this further. Now 2 to the power 0th parent, which is the first parent of x, is this thing and y is this thing. So take anything for reference. So we're taking x for reference. You can also take y for reference. And this node is not a direct parent of x, and it is a direct parent of x but not a direct parent of y. Or if this node is an ancestor of x but is not an ancestor of y, in that case what you do is, if this was my node u, we actually equate this this node to this particular parent, or u is equals to up of u and x. So x was 0. The 2 to the power 0th parent, which was, let's say if this was 1, 2, 3, 4, 5, 6, just a minute, 5 and 6, right? So the first parent was 2 of 5, right? So up of 5th node, and the first parent was 0. This will be 0 actually, because this is not 0 but 2 to the power 0. This is not x but 2 to the power x, right? Remember. The 0th parent of this thing is 2. So what do we say? Is the direct parent, or is the first parent of x or of u a direct parent of x but not a direct parent of y? So sure it is. So now u will become this thing. U is now the node with value 2, right? And now the direct parent of this particular node is the lowest common ancestor, which is true, obviously, right? See over here, the direct parent of this particular node is this thing, which is the lowest common ancestor of x and y. We have arrived at the solution, right? So how exactly does it work is, we use the same binary trick. If 2 to the power 3, which is 8, is a direct parent or direct ancestor of node u and v, then if we initialize u with this thing, then we will have no way of coming back, right? Because if this was something like this, like something like this, so like we have, if this is a direct parent of, let's say this was u and this was v, so this is a direct ancestor of u and v, right? So if we initialize this with u, now I have no other, now I don't know if this is a ancestor or not, because if it would have been something like this also, I need to find the lowest common ancestor between this and this, and now this we're comparing it with this thing. So this is u and this is v, and let's say I'm comparing it with the fourth parent, right, which is this thing. Now this is a direct parent of u and this is a direct parent of v, but this is not a lowest common ancestor. That is exactly why we don't actually do anything if this is a direct parent of u and direct parent of v. If this is a direct parent of u and direct parent of v, don't do anything. Similarly, just similar to the way when we were constructing the binary thing of 13, if this thing is greater than 13, which is 16 is greater than 13, then don't do anything, just decrement this further, right? So similarly, if this thing is a direct parent, a direct ancestor of u and direct ancestor of v, then don't do anything, just decrement this further. If x was 3 and 2 to the power 3 is 8, then decrement that further with 2 by 1, right? So this will become 2. Now check 2 to the power 2, 4. Is the fourth parent of u a direct ancestor of u and a direct ancestor of v? If it is not, then move u to the fourth parent of it, right? So we'll see, we'll just see over here with the example. I've actually made a tree over here, right? So now let's say I need to find the lowest common ancestor between this 9, or say, yeah, this 9 and this 8, right? So now the up, let's say the up of 9 of 0, the 2 to the power 0th element, which is the first element, is 5, right? Then the first parent of 9 is 5. Up of 9 of 1, which is 2 to the power 1. 2 to the power 1 is what? 2. So the second parent of 9 is 2, so which is 2. Now up of 9 and 2, which is 2 to the power 4. So there is no fourth direct parent, so we'll take the last element which was possible, which is 1. So this is 1. Similarly, we can do this for all the elements greater than this also, right? Okay. So now similarly we'll write for the 8th element. So up of 8 of 0 is 4, right? Up of 8 of 1, which is 2 to the power 1th parent, is 1. Up of 8 and 2 is 1 again, because this is the highest node, will not do anything, right? So now the highest power, let's say for example x was 3. Now let's consider, and okay, I'll just write one more over here. So this is up of okay, I chose the wrong color. So up of 9 and 3 would be 1, so because 1 is the highest possible. And similarly for up of 8 and 3 would be 1 as well. Okay, I hope this makes sense. Cool. Okay, so now x is equals to 3. We check the 2 to the power 3th parent, which is the 8th parent of this thing and this thing. What is the 8th parent? Let's say I'm considering with the respect of u. This is my u, this is my v. What is the 8th parent of u, which is first element, this thing? Is this a direct ancestor of 9 and 8? Sure it is. Decrement x by 1, which is 2. Now check the fourth ancestor of, or fourth parent of 9, which is 1, right? So is 1 a direct parent of u and v? Sure it is. Decrement is it further. 1 is 2 to the power 1. Check the second parent of 9. The second parent of 9, which is 2, right? This thing. Is this a direct parent of u and v? It is not. No. So now take this u and take this over here and decrement x by further, one step further, right? We'll keep decrementing x. Okay, because if we do not decrement it, it doesn't make sense, right? You have to decrement it. If you do not decrement it, you know, in the next case, again it will be right, like you will encounter an element which is a direct ancestor of both the thing, then you'll decrement that. So you are just increasing the number of operations. I hope you're understanding, by the way. Okay, so now I'll check for x equals to 0, which is the first parent, 2 to the power 0th parent or first parent. So the first parent of 2, this thing, the first parent of 2 is 1. Is 1 a direct ancestor of u and v? Sure it is. Will not do anything. U will be this thing. Now my answer, the lowest common ancestor, or my answer will be stored in the final value of u and the zeros, 2 to the power 0th parent, or the first parent of this thing, right? This is my answer, and you will see that the lowest common ancestor of 9 and 8 is this thing only. And now we have gotten an answer. I hope it makes sense. So we are just doing the binary operation, as every number can be represented in its binary form, right? So I'm saying that this length can also be written into binary form. The length to the root, or the length to the lowest common ancestor is what? 1, 2, 3. 3, right? 3 could be represented in binary form also, right? As 1 and a 1. So first we'll take 2 to the power 1 thing. So we took this thing, right? And then you'll take this thing, right, which we took at the very last, this thing. So I hope this makes sense to you. I hope you understand the story, right? And yeah, I hope it makes sense. I tried my best to explain this. If just in case if you do not understand this, I would highly recommend you to start from the part where you dropped off from, and I'm sure you will probably get there. And I've written decent notes for this, just in case if you want to read it. So you'll get the notes link in the description. You can refer to it if you want. And essentially, in the end, what we're actually calculating is, we're just calculating the last node, which the direct parent would be the lowest common ancestor, right? So we're calculating the last node, right? Or essentially, if the distance from node u to the lowest common ancestor is k, right? So we're calculating the k minus 1th node, right? The k minus 1th parent of u. That is exactly what we are doing. So let's say if the distance was 3, right? In this case, the distance was 3. So 3 minus 1 is 2. So we're calculating the second parent to 9, right? That is why the binary representation of 2 is 1 0, and that is why exactly why we did an operation over here when the value of x was 1, right? That is exactly why we did it. So I hope you are feeling this concept, you are understanding it very well. So I've written down the steps. First, we will need to obviously calculate the in and out time for each node, because we need to also check if node u is a direct ancestor of v, or a v is a direct ancestor of u, right? If our query would have came like calculate LCA between 3 and 6, then obviously 3 comes before 6, right? Or like 3 is a direct ancestor of 6, right? So in that case, we'll need to utilize this. So that is why exactly why we are calculating in and out time for each node by running a DFS. Now for each node, firstly check if u is a direct parent of v or v is a direct parent of u. If it is, then you know the LCA. Don't do anything. If it is not, calculate the highest power of 2. That could be the CL of log base 2 of n, right? And similarly, I've written down what I've just said. If up of u of j is an ancestor of v, then because we are calculating with respect to u, then like this is node u, this is node v. Just a minute. This is the node u, this is the node v. So now I'm calculating with respect to u. You can calculate with respect to v, it doesn't matter. So I'm calculating the parent of u. So if it is a parent of u, then that means it is an ancestor of u. So just check if it is also ancestor of v, then decrement x or decrement j. Otherwise, if it is not a direct ancestor of v, then you initialize u or change u with up of u and j, of u and j. I hope you get this. This is the implementation for this problem. T in is the end time of particular node. You increment the timer. T out is the out time for this node. We do this at last after processing all the nodes, right over here. And now we're constructing this up array. So up array, say up of u and 3. Let's say so 2 to the power 3 is 8. How we will calculate is, so we can if we want to calculate the 8th parent, so we could calculate the 4th parent and take the 4th parent of that also. That would make 8. So do what? Do a up of u and the 4th parent of this thing, which is 2. So whatever we get from there, we'll calculate the second parent of that also, or the fourth parent of that also. So if you want to calculate the 8th parent, firstly check what is the 4th parent, and whatever is the 4th parent, right, calculate the 4th parent of that 4th parent. So that is exactly what we do over here. Up of v, I minus 1, I is the parent, so I minus 1, and I minus 1 of that particular thing, right? I hope you get this. and now we're calling the DFS for all the children, right? Now, okay, this is the LCA function which works in logarithmic of n, or order of log n for each query, log base 2 of n, just to be precise. We check if u is an ancestor of v, or if v is an ancestor of u. We've written the same thing over here, which we just discussed. If the in time of u is before than v, and the out time of v, out time of u is larger than out time of v, then u is a parent of v, or u is an ancestor of v, because u is coming before v and u is leaving after v. So that means u is the ancestor of v. So we check if u is an ancestor of v or v is an ancestor of u. If it is, then we already know the LCA. If it is not, then we check the highest power of 2 which could be there. If it is not an ancestor of v, right? If it is not an ancestor of v, because we are calculating in terms of u, right? We are calculating in terms of u, so it is a direct parent, or it is a direct ancestor of u. If we just need to check if it is a direct ancestor of v as well. If it is not, then we change u to what we have just discussed, right? And at last, the answer would be stored in the direct parent of this thing. That is exactly how we do this. I hope you get this. And yeah, this was all that you need to know about binary lifting. We are just in time. It's about 35 minutes, and I really hope that you get this, and I hope you enjoyed this. Just in case if you had any doubts, anything, if you want to refer to notes, or you want to know something else, just comment in the video, and I'll be sure to reply to you, right? So till next time, I had actually a lot of things planned on this channel, and so yeah, we're going to be discussing a lot of things over here. So stay tuned, and I'll see you guys in the next one, I'm sure. So bye bye and take care. Thank you.